Okay, in this video, I would like to prove the existence of the Fibonacci limit, not just its value. Let me write down the Fibonacci numbers. Everybody knows them. And I'm going to let those be known by F0, F1, F2, F3, etc. So we have F0 equals 1, F1 equals 1, F2 equals 2, and then whenever you do F sub n, that'll equal F sub n minus 1 plus F sub n minus 2. So that's the defining characteristics of this sequence. Now, let capital Fn equal little fn divided by little fn minus 1. Then the capital Fn's form a sequence. And I guess we'll call this theorem that I'm talking about the sequence capital F sub n converges. This is the part you never seem to see anybody talk about in their videos, so that's why I'm putting it up. Alright, so when you look at sequences, one of the ways you can prove that a limit exists is to prove that the sequence is a Cauchy sequence. So the claim here is that F sub n is a Cauchy sequence. And then what you typically look at in Cauchy sequences is something like this. Now what I'm going to do is assume that n is bigger than m for these computations. Since they're an absolute value, it wouldn't matter, to be honest. You wouldn't lose any generality if you assumed n was bigger than m. So let me go ahead and write this stuff down. We have fn over fn minus 1 minus f sub m over fm minus 1. Then I'm going to get common denominators. Well, actually, I'm going to cross multiply and get fn fm minus 1 minus fn minus 1 fm. And that's all divided by fn minus 1 times fm minus 1. Now here's the big result. You are probably not going to believe this, but this actually equals f sub n minus m minus 1 divided by f sub n minus 1 times f sub m minus 1. I will prove this later. I'll do that at the end of this proof. I just wanted to get this through. I also wanted you to be able to pause the video and maybe try to solve it on your own with a hint or two before watching me actually sail through the whole proof. Now, this, I'm going to rewrite this as f sub n minus m minus 1 divided by f sub n minus 1 times 1 over f sub m minus 1. Now, one of the things you should know, or it's easy to prove, is that f sub n, the little f's, is an increasing sequence. That is extremely easy to see. So what that means is that fn minus m minus 1 is most definitely less than fn minus 1, because that m is greater than or equal to, well, 1. And no matter what, when I'm talking about limits, I'm talking about large values of n and m anyway, so m is most definitely not a zero number. So this is less than or equal to 1 times 1 over f sub m minus 1. And not only that, f sub n goes to infinity as n goes to infinity. That means that this here, well, let me write this. As m goes to infinity, this will go to 0. And so you've proven that you have yourself a Cauchy sequence. Now, if you want to do it like a formal proof, you can do this. Let epsilon greater than 0 be given. So what I'm going to do is call this the formal proof. Let m be a natural number such that 1 over f sub capital M minus 1 is less than epsilon. Since the fn's go to infinity, this is quite possible. I believe it's referred to as the Archimedean property, but you'd have to check it out if you want the words to it. So then, if m and n are greater than this capital M, we have f sub n minus f sub m is less than 1 over f sub m minus 1, which is less than 1 over f sub m minus 1. So let me show you why that's true. We have f sub m minus 1 would be greater than f sub capital M minus 1 because I'm choosing m to be bigger than the capital M, and we know this is an increasing sequence. So when you take 1 over these items, it switches the inequalities. And both of my m's look exactly the same. Let me make sure one of them looks lowercase. I'll put 3 humps for that one. So if that'll help. And this m over here is a capital one, so let me fix it. M minus 1. Of course, that is equal to epsilon. And that will do it for the Cauchy portion of it. Now for the other portion, that is my little trick here. This is where f sub m minus 1 minus f sub n minus 1 f sub m equals f sub n minus m minus 1. The whole proof relies on that particular result. And this is seriously just a matter of manipulation. So I'll show you what I'm talking about. We're going to start with f sub n, f sub m minus 1, minus f sub n minus 1, f sub m. Now what I'm going to do is called step outer. So let me show you what I'm going to do. The f sub n I am going to expand as such. So what I've done here, follow along, I've expanded this fn out here and this fm out here. So I'm calling this step outer. So that was step outer for that. And notice what happens. It's designed to cancel things out. So what it'll leave you with is f of n minus 2, f of m minus 1, minus f of n minus 1 times f of m minus 2. Now I'm going to do step inner. And if you can guess, that's where I'm going to attack the inside f's. And I'm going to expand those. Now here we're going to cancel again. See the f of n minus 2 and the f of m minus 2? There it is again, so I'm going to get rid of those. And I have f of n minus 2, f of m minus 3, minus f of n minus 3 times f of m minus 2. Now remember, this was the original f of n, f of m minus 1, minus f of n minus 1, f of m equals that. So this is what I need you to notice. Look at the indices before I did this. N went down by 2. The m also went down by 2. This n minus 1 also went down by 2. This m went down by 2. So after doing an outer and then an inner step, I'm able to reduce all of the indices by 2. I'm going to do it again. So once again, we are going to do a step outer. That's where I attack the outside. And cancel what's obvious. The n minus 3, m minus 3's cancel. And we have f of n minus 4, f of m minus 3, minus f of n minus 3, f of m minus 4. Now I'm going to do my step inner. This is where I expand the inside f's. So I'll have f of m minus 4 plus f of m minus 5 minus f of n minus 4 plus f of n minus 5 times f of m minus 4. Now I see f n minus 4, f m minus 4 can cancel. And we're left with f sub n minus 4, f sub m minus 5, minus f sub n minus 5, f sub m minus 4. And let me put our original back again. So you can see now my indices, I've dropped the n attached to the f here by 4. m minus 1 has been reduced by 4. n minus 1 has been reduced by 4. m has been reduced by 4. So you can see each time I do an outer-inner step combo, the indices drop by 2. Try it again. You'll see what I'm talking about. It's kind of fun. So let the combo of inner and outer steps be called a two-step. Thus, this is what we have. After k two steps, this is what our equation is. F sub n, f sub m minus 1, minus f sub n minus 1, f sub m. That'll equal f sub... I'm going to make my letters big so that you can see all these things. Each time you do a two-step, you reduce the indices by 2. So if you do this k times, then this is the result you're going to get. Alright, so now I'm going to key in on a couple of things. Case 1, m minus 1 is even. So if m minus 1 is even, I'm going to let k equal m minus 1 over 2. So it's an integer, or the whole number. And so what we get in that case is we get f sub n, f sub m minus 1, minus f sub n minus 1 f sub m. That's going to equal f sub n minus 2 times m minus 1 over 2. These subscripts get complicated, but they're not terrible. So everywhere I see a k, I'm just going to put an m minus 1 over 2. Keep in mind that the whole time I am working with the fact that I'm assuming that the m's are smaller than the n's, and since they're an absolute value, it really doesn't matter which one you assume that on. Let's see, we're going to have n m minus 2 times m minus 1 over 2. And so if I cancel these 2's out here, here's what I'm left over. I want to be really careful here so that you can see these subscripts, because obviously if a mistake is made, somewhere in here is going to be the culprit. And now let me go ahead and simplify each of these things. I have f sub n minus m plus 1, f sub 0, the m minus 1's canceled there. Then I have f sub n minus m times f sub 1. Well, these are easy. We have f sub n minus m plus 1, f0 is 1, minus f sub n minus m, f1 is also 1. So we have f of n minus m plus 1 minus f of n minus m. Now I'm simply going to expand that f sub n minus m plus f sub n minus m minus 1 minus f sub n minus m. And we can take out the f sub n minus n's, and we get f sub n minus m minus 1. Now that was the assumption that m minus 1 was an even number. On the other hand, what if m minus 1 is odd? So this is case 2. And so let me write my equation that we have up again. So we had f sub n minus 2k, f m minus 1 minus 2k, minus f of n minus 1 minus 2k, f of m minus 2k. I'm going to let k equal m minus 2 over 2. So since m minus 1 is odd, m minus 2 is an even number, and it is smaller, that's what I want to work with. I don't want to overwhelm the n's by having m's bigger than it, because then when you whittle it down, it may not work out right. Although I have a feeling that I never did have to make that assumption. I have a feeling these will whittle down regardless. But nonetheless, let's go ahead and throw in those numbers. So when I put those in, I'm going to get f sub n minus 2 times m minus 2 over 2. F sub m minus 1 minus 2 times m minus 2 over 2. I think I might be running out of space here. Let me give this some more. Minus f sub n minus 1 minus 2 times m minus 2 over 2. Let me fix my n to make it look more n-ish. And then we have f of m minus 2 times m minus 2 over 2. And so let's go ahead and do all of our cancelings. And we have f sub n minus m plus 2, f of m minus 1 minus m minus 2, minus f of n minus 1 minus m minus 2, f of m minus m minus 2, f sub n minus m plus 2, f sub 1, m minus 1 minus m plus 2 is f sub 1. We have f sub n minus m plus 1, and then we have f sub 2. So let me put in the numbers that I know. This is f sub n minus m plus 2 times 1 minus f sub n minus m plus 1 times 2. So this equals f sub n minus m plus 2 minus f sub n minus m plus 1, but that's 2 times that. So let me go ahead and expand index f sub n minus m plus 1 plus f sub n minus m minus 2 f sub n minus m plus 1. So I can take out one of those, so I get f of n minus m minus f of n minus m plus 1. Now let me expand that plus 1, f of n minus m minus f of n minus m plus f of m minus n minus 1. Those will cancel, and we get negative f of m minus n minus 1. So that, in absolute value, f of n, fm minus 1 minus fn minus 1, fm equals fn minus m minus 1. I think I've got right here, be careful, I got my indices mixed up. I'm surprised this didn't happen earlier. N minus m, and let me fix this here because the whole result relies on this. And so now, with that, therefore, limit as n goes to infinity, fn exists. If you need reminding, the real numbers are a complete metric space under the normal metric topology. So in complete metric spaces, if you can show a sequence as Cauchy, that is equivalent to showing that it exists. And then finally, to get the limit itself, let L equal the limit as n goes to infinity, capital F sub n. Alright, then the limit as n goes to infinity, little f sub n over little f sub n minus 1 is equal to L. So then we have the limit as n goes to infinity, f sub n minus 1 plus f sub n minus 2 over f sub n minus 1 is equal to L. Let me break up that limit, or break up that fraction. N goes to infinity. F of n minus 1 over f of n minus 1 plus f of n minus 2 over f of n minus 1 equals L. Of course, that's the limit as n goes to infinity of 1 plus, well, I'm going to do this, 1 divided by f sub n minus 1 divided by f sub n minus 2. And that is equal to L. If I break in the limits, then I'm going to get 1 plus the limit as n goes to infinity, 1 over f sub n minus 1 over f sub n minus 2 equals L. Well, that limit down there, that is 1 over L. And then multiply through by L, and we will end up getting, I'm going to put everything over here, L squared minus L minus 1 equals 0. Use the quadratic formula. L equals 1 plus and minus the square root of 1 minus 4 times 1 times negative 1. All of that divided by 2 times 1. And you're going to throw out the negative solution here because all of the numbers involved in this limit were positive, so the negative doesn't make any sense. So the only one that we want to keep is 1 plus the square root of 5 divided by 2. And everybody knows that famous number.